Hello everyone, welcome to worked example 5.13 on page 216 for the section 5.2, heating effect of electric currents. So part A, determine the total resistance of the circuit shown below, and then B, hence calculate the current and power dissipated in each of the resistors. So we've got our diagram here. Now I hope you have your formula booklet handy. Let me just grab mine. So I hope you recognize the circuit symbols, but in case you don't, this rectangular box here, that is a resistor. So remember, resistor either will be represented like this or like that. Okay, so either one of those. So here we have the rectangular symbol. We've got a battery here, right? So it's just given the cell symbol, which is fine. We're given the EMF, that's the voltage of the cell, and that's the total voltage in the circuit, 6 volts. So actually, let me start by writing all this down. So epsilon, which is the total voltage, is 6 volts. We know various resistances. Notice that each of the resistors has a different resistance. In the lesson, we didn't specifically look at that in the video, rather, but here we're going to deal with that. So I'll show you how to solve this type of problem. By the way, and I know I'm going to sound like a broken record when I say this, but this is the type of problem that would be covered in grade 9 science. At least part A and the first half of part B to calculate the current. But realistically, calculating the power is simple once you have the current. All right, so we have total voltage. What we have here, this is what's known as a combination circuit. Sometimes it's called a mixed circuit. Okay, so it can go by either of those names, but all that means is it's not just series, it's not just parallel. It's a combination, series, and parallel. So the goal with these kinds of things, and because this is a combination, series, and parallel, you can't just jump to the formula sheet and, so let me just find the page. You can't jump to the formula sheet box 5.2 and then use one of these formulas for R total. Not from the get-go, and definitely not for all the resistors, because they're all connected a bit differently. Okay, we've got the 2 and 3 ohm resistors connected in parallel, and those two are connected in series with the 1.8 ohm. So what I'm going to want to do is merge these two, figure out what the equivalent resistance of these two would be as a single resistor, and then that single resistor will be in series with the 1.8. But before I actually do any actual math, I'm going to label these because usually in the question they're not labeled, but I'm going to have to use subscripts in my calculations. So I'm just going to label these 1, 2, and 3. Okay, so that means R1 is 2 ohms, R2 is 3 ohms, and R3 is 1.8 ohms. So like I said, the first step is I'm going to take these two pieces and I'm going to merge them into one single resistor. And since these two, R1 and R2, are in parallel, I can use the formula for a parallel resistance. So that one, this one right here, the second one from the bottom, I can use that formula to figure out the equivalent resistance of these two. So the way I'm going to represent it is this. I'm going to say that 1 over R12, so R12 is going to be the equivalent of these two, is equal to 1 over R1 plus 1 over R2. And I actually just want to show you what this new circuit would technically look like, this simplified circuit. So we would have, so here would be our junction where it normally would split, but now I have a new equivalent resistor. And then we have the original 1.8. And we have our 6-volt battery. Okay, so 6 volts, 1.8 ohms, and this is resistor 3. This is equivalent resistor R12. All right, so this is what I'm trying to say. We merge those into a single resistor, and this is where we're going to calculate it. So 1 over R1, so that's 1 over 2 ohms, plus 1 over 3 ohms. Keep in mind that's equal to 1 over the equivalent resistance. So 1 divided by 2, I mean, that's 0.5, but let's just do this properly. Plus 1 over 3, so that's 5 over 6. Right? So 5 over 6 is equal to 1 over R12. So that means R12 over 1 is equal to 6 over 5. So 6 divided by 5, I mean, that's 1.2. So 1.2 ohms is this equivalent resistance. Okay. Now, what we're going to do is merge these two resistors into a single resistor. What we're trying to do right now, by the way, is find the total resistance of the whole circuit. Excuse me. So that means if we were to replace all three of these resistors in this configuration with a single resistor, what would it look like and what would the resistance be? So now we're going to combine these two, and since these two are in series with each other, and let me just label these ones, these are in parallel, just these two were in parallel and these two are now in series. That means I'm going to calculate the total resistance, which is R123. Now, because these two are in series, I just have to add them up. So R12 plus R3, so that's 1.2 ohms plus 1.8 ohms, which is 3.0 ohms. And R123 is the total resistance. Those two are the same thing. So now what we have is, because we don't need as much wire, we have one resistor, and we have our single battery. So this is 6 volts, and this is R123, also known as our total, which is 3 ohms. Excuse me. Okay. Now, the whole point of part A was to find the total resistance. So we did that. So the total resistance in the circuit is 3 ohms. So therefore, the total, and I guess we should label this part A. Therefore, the total resistance in the circuit is 3 ohms. Okay, and that's our answer for part A. All right, so moving on to part B. Calculate the current and power dissipated in each of the resistors. Okay, so we'll figure out the power once we figure out the current. So that'll just fall into place very easily. But let's figure out how we're going to determine the current. So we know the resistances, right? R1, R2, and R3. I now know the total resistance going through the circuit. But guess what? With total resistance and total voltage, guess what I can find? I can find total current. Okay, so remember that the short side represents the minus and the long side represents the plus. And unfortunately, due to an old system, we draw the current going from the positive side. Now, regardless of that, so we know the current's coming like this. Honestly, regardless of which way you're going to draw it, I mean, other than potentially losing marks if you draw conventional current the wrong way, the mathematics works the same both ways. So just letting you know that now. Okay, so this current's coming out of the battery. It reaches this junction right here, and then the current splits. Okay, so by the way, the current that's coming out of the battery is I total. So I total makes it to this first junction. It splits. Now, if those two resistors had the same resistance, it would split evenly. Half would go here and half would go here. And then they would recombine at this junction back into I total. Now, I total goes through resistor number 3, and then it comes back to the battery. Okay, so if you were to actually label the current going through resistor 3 as I3, what you'll notice now is that I3 and I total are the same thing. Now, just because I total is not splitting evenly between these two doesn't mean we can't figure out how much current is going through one and the other. We will calculate that. In fact, you already have an idea which one will have the higher current. The more resistance that there is, so for the 3 ohms here for R2, the less current there will be. So you'll have more of it going through R1 than R2. Okay, so we have to find the current in each of the resistors. So, I mean, the first one we can just state right off the bat. I know I3 is equal to I total. Let's find out what I total is. So, using Ohm's law, V is equal to IR. I know that current is equal to voltage divided by resistance. And since I'm looking for a total current, I'm looking for total voltage over total resistance. Now, total voltage, that's the 6 volts. And total resistance I just found, so that's 3 ohms. Everything's SI, so I plug them in. 6 divided by 3 is 2, so that's 2 amperes. Total current is 2 amperes, which means current through resistor 3 is 2 amperes. So therefore, I3 is equal to 2, oh, not ohms, amperes. Oh. Amperes. Okay, so now we have to figure out how much of that 2 splits into the 2 and how much goes into the 3. And so to do that, we're going to consider what happens when these two got merged into a single resistor. We're going to need the voltage. Okay, so we're going to need the voltage drop across 2 and 3. And actually, this is a good time to point out that since R1 and R2 are in parallel with each other, what you would know about parallel circuits is that they have the same voltage, right? So whatever voltage you have here, you've got the same voltage here, regardless of regardless of the resistances. If they're parallel, the voltages are the same. So whatever voltage I calculate here for R12, this one will have the same voltage and that one will have the same voltage. Okay, so let's figure out what the voltage is for R12. I know what the resistance is, and I know what the current going through it is. The current going through it, I12, is equivalent to the total current. And the total current is, where was it? 2 amperes, right? So we've got 2 amperes going through there. We know the resistance, so let's find the voltage. So voltage 12, which is going to be the same as voltage 1 and the same as voltage 2, that's going to be equal to IR, right? That's Ohm's law. So that's equal to 2 amps times 1.2 ohms. So 2 times 1.2 is 2.4. Okay, I definitely did not need the calculator for that. 2.4 volts. Okay, so 2.4 volts is therefore the voltage drop across R1 and also R2, right? So V1 and V2 are also 2.4 volts. Now, why is that important? That's going to help us find the currents. So current is voltage over resistance. So current through 1 is going to be voltage 1 over resistance 1. So that's 2.4 volts divided by 2.0 ohms. So 2.4 divided by 2, that's 1.2 amperes. So I1 is 1.2 amperes, and I2 is V2 over R2. So 2.4 volts divided by 3 ohms. 24 divided by 3 would be 8. So this would be 0.8 amperes. Okay, so therefore, therefore the current in each resistor is 1.2 amps, 0.8 amps, and 2.0 amps. Now, the fact that I have everything labeled in the original picture, 1, 2, 3, that corresponds to my subscripts. If I don't label anything in the picture and I all of a sudden start using subscripts, it is not a proper way of showing your work, and it does not show that you understand what it actually applies to. So please keep your work as organized as possible. All right, so we've got that. The last step is to figure out the power dissipated in each of the resistors. All right, so power, if you grab your handy dandy formula sheet, power is equal to V times I, or I squared times R, or V squared over R. It's up to you which one you want to use. Since the question made us find current and gave us resistance, I'm just going to use I squared times R, but realistically any of those could work. And while we're at it, let me just call this part B. Okay, so P1 is equal to I1 squared times R1. So I1 is 1.2 amps. It's 1.2 squared times R1, which is 2 ohms. So 1.2 squared times 2, that's 2.88 watts. Now P2 is equal to I2 squared times R2. I2 is 0.8 amperes squared. R2 is 3 ohms. So 0.8 squared times 3, 1.92 watts. And finally, P3 is I3 squared times R3. So what do we have? I3 is 2.0 amps squared. R3 is 1.8 ohms. 2 squared is 4, and then 4 times 1.8 is, let's see, 7.2 watts. So therefore, the power dissipated across each resistor is 2.88 watts, 1.92 watts, and 7.2 watts. And of course, depending on the problem, if it asks us to round to a certain decimal place, we can do that too. All right, so that's it for this worked example. Stay tuned for one more worked example in section 5.2.